Welcome everybody to lecture 1.3. Today's discussion is going to be about vertical asymptotes, and without further ado, let's jump straight into it. A vertical asymptote is going to be present in rational functions only. So whenever you have a rational function where it's going to appear such as this, where it is you're going to have a numerator and a denominator, that's the definition of a rational function, and the denominator is approaching 0, wherever it is that the denominator is going to be equal to 0, that's where the function is going to be undefined, and that is where it is that you are going to find your vertical asymptote. So say I wanted to draw this out, and we had the function 1 over x. We can tell that the function is undefined at x equals 0, because you can't divide by 0, and because of that we're going to have a vertical asymptote, which is going to be shortened out as VA, at x equals 0. Now, if your function happens to fall within one of the following criteria, which it is that I'm going to write out right now, you're going to have a vertical asymptote at whatever that a value is going to be. So let me write these out, where it is that And with all of that being said, basically wherever it is that you find either a right-handed limit, a left-handed limit, or an absolute limit of a function that is going to tend towards infinity, that's where it is that you're going to find a vertical asymptote. So, as we mentioned earlier, for the function 1 over x, the function fails to be defined at 0, and because of that, we're going to have a vertical asymptote, because from the right, it's going to tend towards positive infinity. This is heading in the direction of positive infinity, and over here it's heading in the direction of negative infinity. So it fits two of these criteria right over here, where it is that the left-handed limit tends towards negative infinity, and the right-handed limit tends toward positive infinity. So if it falls within any of these categories, you are going to have a vertical asymptote at whatever that value is. So without further ado, let's jump on to couple of practice problems. This is going to be a really easy section. Oh, look at that, we're already pretty much done actually for the most part. Imagine we have the function f of x is equal to 2x over x minus 3. Well, we just mentioned that wherever it is that the denominator is going to be equal to 0, that's where it is that we're going to find a vertical asymptote. So if we wanted to find a value that's going to make the denominator equal to 0, well, all we really need to do in this case is we need to plug in 3. So we can come to the conclusion that there is a vertical asymptote at x is equal to 3. Now, just like anything else, there's always going to be a couple more complicated problems, but vertical asymptotes are pretty straightforward. There's not really much work into them. All you really need to do is set the not set the derivative equal to 0. That's later on in the course, but keep that in mind. Whenever it is that you're doing calculus, set the derivative equal to 0. That's going to be the solution 90% of the time. Now, failure to be defined does not necessarily mean that there's going to be a vertical asymptote present on the graph of the function. Consider the following function right over here. F of x is equal to the square root of 2 minus x. This function fails to be defined for all values that are going to be greater than positive 2. So if we try plugging in a value which is going to be greater than positive 2, then it's going to be undefined because you cannot take the square root of a negative number. But that does not necessarily mean that you're going to have a vertical asymptote at that value. It's only for rational functions. So undefined does not mean vertical asymptote. It only means vertical asymptote in the circumstances that you have a rational function. A function like this is not a rational function, and because of that, it's not going to have a vertical asymptote. So we're going to do 3 practice problems and we're going to wrap up. This is a really short video, really easy stuff. So we're going to find the x values where it is that there is a vertical asymptote for f of x is equal to x squared plus 1 over 3x minus 2x squared. Now, in this case, the numerator is completely irrelevant. We really do not care about the numerator. All we need to do is we need to set the denominator equal to 0, and that's where it is that we're going to find our vertical asymptotes. So say we wanted to factor this a little bit. The numerator doesn't matter, we can leave it alone. We can factor out an x out of the denominator. So we can factor out an x, and it's going to leave us with 3 minus 2x, which leaves us with two distinct factors, If either of these is going to be equal to 0, then the entire function is going to be equal to 0. So one of the solutions is going to be equal to x equals 0, because if we were to plug in 0, then this would go to 0. 0 multiplied by anything is going to make the denominator equal to 0. And we have another function right over here, which is going to be 3 minus 2x is equal to 0. Now we can go and rearrange this to 2x is equal to 3. X is going to be equal to 2/3. So at x equals 0 and at x equals 2/3, this function is going to have a vertical asymptote. Next up, we've got f of x is equal to 2x plus 1 over x cubed plus 2x plus x. What is it that we can do in this case? Well, we're going to be doing exactly the same thing as we did in the previous problem, where it is that we're going to be factoring an x out of the denominator. We want to simplify it as much as we can, so this can be rewritten as 2x, I'm going to need to get a new marker soon, 2x plus 1, and we can factor an x out of this, and it's going to leave us with x squared plus, oh, this is a 2x squared actually, x squared plus 2x plus 1. Now we can factor this function even further and rewrite this as 2x plus 1 over x times x plus 1 times x plus 1, or x plus 1 squared, whatever it is that you prefer. And in this case we're going to have two solutions because, well, this is going to be the exact same thing, so we can compress this a little bit more into 2x plus 1 over x times x plus 1 squared. So in this case we want to find the two values that are going to make the denominator equal to 0, and we know that x is going to be one of them. X is going to be equal to 0 because 0 times anything is going to give you 0 in the denominator, and x plus 1 is also equal to 0. That means that x is equal to -1. So at x equals 0 and x equals -1, there is a vertical asymptote for this function. And finally, last example. I'm telling you guys, vertical asymptotes, really easy stuff, but it's going to give you the foundation for what it is that you need for graph building, which is going to be later on in this course. So we have the following function, which is f of x is equal to 3x squared minus 9 over x squared plus 7x plus 12. Now we want to set the denominator equal to 0. What we can do in this case is, whenever it is that I see something that can be factored out, I'm going to factor it out immediately. So I'm going to factor the numerator, I'm going to pull out a 3, and that's going to leave me with x squared minus 3. This is not actually necessary because all we're doing is setting the denominator equal to 0. And we can factor the denominator as we want two values that are going to give us a sum of 7 and a product of 12. Sum of 7 and product of 12, I think 3 and 4 work out for that case. So we're going to have x plus 3 and x plus 4. So our two equations that are going to set the denominator equal to 0 are going to be x plus 3 and x plus 4. So we write out x plus 3 equals 0 and x plus 4 equals 0. We drag the 3 to the other side. This means that x is going to be equal to -3, and this means that x is equal to -4. So these functions are going to have a vertical asymptote at, this function over here is going to have a vertical asymptote at -3 and -4. And that's about it for this lecture. There really isn't much to say about vertical asymptotes. It really is quite that easy. All you need to do is set the denominator equal to 0 and find the values that make it happen. Most of the time, all you really need to do is do a little bit of factoring. Sometimes you can cancel something out in the numerator, but most of the time that's not necessarily the case. But keep an eye out for that. And with all of that being said, I will see you guys in the next video. And this time we will actually be discussing continuity. I've been talking about it for the past 3 lectures. Next lecture's continuity, next lecture's continuity. Next lecture is actually continuity. I wrote it up last night, so I know exactly what's going on. Have a nice day.